All right, yeah, so this is continued applications from yesterday, and we're going to kick it off with Sarah Baker, who is here from the U.S. Bureau of Reclamation, who's going to be talking to us about the Colorado River Basin testbed.
Thank you, everybody. As Erin said, I'm with the Bureau of Reclamation in the Research and Modeling Group here in Boulder, Colorado. And today I'm going to be talking about the Colorado River Basin Operational Projection Testbed, which was part of my PhD and worked on at CU with Balaji Rajagopal, as well as Andy Wood from NCAR. So I'm kind of going to jump into things. This is the summary of the basin-wide models we have in the Colorado River Basin for water management. We have the Colorado River Midterm Modeling System, which is called CRIMS, and we have this Colorado River Simulation System, or CRSS, and those are used for two different types of applications. CRIMS is used for official operating protocols, and then CRSS is used for long-term planning and NEPA type studies. CRIMS can be operated in two different types of modes. I'm going to focus on the ensemble mode since with the testbed, we use probabilistic forecasts, and CRIMS in ensemble mode has those capabilities. CRIMS can run out from 1 to 5 years. For this specific application, we're going to be focusing on the 2-year range. So one of the main inputs to CRIMS is streamflow forecasts. And as we all know, streamflow forecasts are important to both operational models for projecting future reservoir conditions, as well as useful in other applications such as agriculture, municipal, and recreational areas. So most of the streamflow forecasts, or at least the operational streamflow forecasts in the US, are produced at river forecast centers, or RFCs. And the schematic here on the right shows a diagram of how these forecasts are typically produced at RFCs. The RFCs have hydrologic models that they run, that they use to produce streamflow forecasts, and they maintain them on a daily basis. They also could use statistical water supply forecasts, which are a little less common and not used as common in the Colorado River Basin, but other areas in the US depend on them for more information. The other part of these forecasts is that there's, these slightly newer climate forecast techniques that, you guys have been talking about through this workshop. And those are not incorporated in a systematic way into these processes typically. So certain river forecast centers might look at them more than others, depending on the skill they see in them for their specific region. Oops. So the forecasters use these different products to produce an official operational forecast, which they then provide to water managers to make decisions with. And so that's kind of where the motivation for this work comes from. So the objectives of this project were to create a testbed framework and establish a protocol for testing the performance of streamflow forecasts and the associated reservoir operational projections in the Colorado River Basin. So we wanted to first assess how our current streamflow forecasting technique was performing in this Colorado Basin streamflow forecast testbed using the CRIMS model. And then we also wanted to test different experimental forecasts through this testbed as they become available. So this is the general layout of the testbed and how it works. The main input is streamflow forecasts, and I'm going to be discussing 3 different ones today. The first is climatology, and we created an ensemble of climatology based off of the period of record from 1981 through 2010. And this was just resampling in an index sequential method, the historical streamflow, kind of as a baseline to test the other forecasts off of. The next one is ensemble streamflow prediction, or ESP. And ESP is the current operational forecasts that are used in the Colorado River Basin, as well as many other locations in the United States. And then the third is this climate-informed K nearest neighbors method, or CLIME-KNN. And this was an experimental forecast that came out of my PhD work. And so we just wanted to compare these 3 for seeing how they performed both for streamflow forecasts and then operational projections. Also, this has been used through other examples. So for instance, Erin, we worked with her and used the test bed to test one of her forecasts that extended out 5 years, as well as other ones out of CU. So these streamflow forecasts are input to the test bed, and they are run through CRSS from 1981 through 2016 for this specific application. And we do use that in a framework called RiverSmart, which allows you to simulate multiple different streamflow forecasts in an easy way. Then we assessed the results based off 2 different types of metrics. So we have the hydrologic metrics, in which we are looking specifically at Lake Powell unregulated inflow. And we can look at different metrics within that, such as root mean squared error, continuous rank probability skill score, other errors, and biases. And then we also can look at reservoir system metrics. So this includes looking at the different reservoir parameters, such as pool elevation, outflow, or operating tiers. And we can look at the root mean squared error of those, as well as categorical skill scores and other biases. So I'm going to jump into some results. So this is the water year Lake Powell unregulated inflow. We're looking here at the continuous rank probability skill score, or CRPSS. For CRPSS, a value less than 0 means that it's less skillful than climatology. A value equal to 0 means that it's of equal skill to climatology, and a value between 1 and 0 is more skillful than climatology. And for climatology, we're using in the 1981 through 2010 period. On the x-axis here, we have lead time. I'm sorry, it's a little small, but it's from 24 months to 1 month. And I'll go through an example of how to read that here. So here on the left, we have an example of the August 14 water year forecast of 2015. So we're looking at a full water year, which is October through September of flow. And then so as you march to the right in this plot, you decrease your lead time. And once you get past October to a 12-month lead time, you start to have observed flows in the forecast. So inherently, the skill will get better. So on the right here is an example forecast of May 2015, or from May 2015 of the water year 2015 forecast, which would include October through April observed flows and be just forecasting May through September. So generally, you can see there's not much skill in the out year here with any of the forecasts. There's some variability, but the median is around 0. As you get into the fall of the out year, you start to see a slight increase in forecast skill, especially with ESP and CLIMB-KNN. And that's because ESP is starting to have knowledge of antecedent conditions. So in the fall, we know or have a better idea of what the soil moisture is, which can inform the forecast for the remainder of the water year. And then specifically here from December through March, we're seeing a larger range of skill with some lead times, CLIMB-KNN, which uses NMME to weight ESP forecasts, starts to perform in some months slightly better than ESP, but it's not necessarily consistent. It also has a large range, which isn't necessarily desirable. We can also look at root mean squared error for the water year Lake Powell unregulated inflow. And here you can see the range of these different RMSEs. And what stands out is that the CLIMB-KNN does have a slightly smaller error than ESP on the median. And that continues to decrease through the winter and the spring into the runoff season. And so it's important to look at many different metrics because they might tell you something slightly different. And so these are just 2 that we picked out. You could also look at metrics for reliability and spread as well. So the other side of this is looking at the operational projections for the reservoir conditions. And here we have, again, climatology, ESP, and CLIMB-KNN. On the top, we have the Lake Powell end of calendar year or end of water year pool elevation. And on the bottom, we have the Lake Mead end of water year pool elevation. And these are important metrics because they're used in operational decision-making in the basin. So if we look at Lake Powell, we see a kind of similar trend to what we were seeing with the water year streamflow forecasts, where you see that the CLIMB-KNN performs slightly better than ESP, at projecting that end of water year pool elevation, and that continues to decrease, especially by the winter into the spring. And so we can see that in Lake Powell, and the errors are slightly smaller in Lake Mead because Lake Powell is above Lake Mead and has kind of a attenuated result or amount of stream flow that it receives into it. Jeez. So in conclusion, the Colorado River Basin Operational Projection Testbed provides a foundation for the systematic evaluation of inflow forecasts and reservoir operational projections for this basin-wide example. We are illustrating that there are opportunities for improvements in the skill and reduction of error in streamflow forecasts, but there's more to be done to see those come to fruition. We also saw that enhanced streamflow forecasts do translate to improved reservoir operations, though it might not be in a linear way. And in the future, we want to continue to use the testbed to assess different experimental forecasts as they become available with time. So thanks.
Great. Thanks, Sarah. Round of applause. We're going to hold questions till the end. Next, we're going to have Desislava Petrova, who's, I think, joining us online from Climate and Health Program and ISGlobal, talking about multi-year statistical prediction of ENSO.
So good morning. My name is Desislava Petrova, and I'm a researcher at the Climate and Health Group of the Barcelona Institute for Global Health. And today I'm going to talk about a statistical model that was designed to predict ENSO events, especially 1 year in advance and beyond. So the model is based on structural time series modeling, and it's formulated in terms of unobserved components, such as trend, seasonal, time-varying cyclical components, and it can easily be extended with regression effects so that predictor variables can be included. This type of modeling is very effective when complex features are present in the time series, such as mixed frequencies or multiple modes of variability, or also nonlinear processes. So in our ENSO model, we predict the Niño 3.4 time series, and we use a trend component, 2 time-varying seasonal components with semi-annual and annual frequencies. And we also have 4 cyclical components, time-varying, which are typically estimated to have periodicities of near annual, quasi-biannual, or quasi-quadrennial timescales, or also decadal. And as I said, we also have regression predictor variables and noise. On this figure, you can see the evolution of the typical evolution of sea surface temperature and zonal wind stress anomalies, which are involved in these cyclical components. So this is actually correlation between the CUF1 of filtered sea surface temperature and surface wind stress anomalies, and the same anomalies in the equatorial Pacific. So you can see that in all 3 of them, there is the transition between La Nina and El Nino-like conditions. Okay, so as I mentioned earlier, we also include regression variables in the model. And one of the variables is zonal wind stress. And here on this figure, you can see composites of zonal wind stress anomalies with respect to the El Nino peak in boreal winter. And these are anomalies at 2 years before the peak, or 1 year before the peak in the middle panel, or about 6 months before. And we obtain indices from these red boxes here to use as predictor variables. We also use indices of subsurface temperature, also based on composite analysis with respect to the El Nino peak in Boro winter. And here on the left, you see anomalies in the subsurface at different depth levels at very low lead times before the peak of El Nino, so 19 to 28 months before. And on this figure, it's on the left, it's the same, but at shorter lead times of between 7 and 16 months. And we use different indices for predictions based on when the expected peak of ENSO would be in Boro winter, because the subsurface anomalies migrate slowly. And as you can see here, they actually start at the very long lead times in the far western Pacific, and then they migrate towards eastward and upward along the thermocline at the shorter and medium lead times. Okay, and so what I'm showing here is predictions with the model at both long and short lead times at 6 months and 24 months. And what can be seen here is that the predictions improve substantially for the long lead times after 1994, which is when actually the Tropical Pacific Observing System was completed, and there were better observations of the subsurface after this year. And this is seen very well in the middle panel here of the long lead time forecast, especially of the amplitude. And then it's also, you can also see it on the bottom panel, which shows the 16-year moving average root mean square error, and it drops dramatically after 1994. This is also evident in this figure, which shows the predictions of the major El Nino events before 1994 and after 1994. On the left and on the right, and you can see that the amplitudes of the major El Nino events are much better predicted for the events from the more recent period as compared to the period before 1994. Okay, so now I'm going to talk a little bit about the application, about an application of our El Nino forecasts. And we apply them for the forecast of dengue fever in a big city in Ecuador called Machala. Dengue is endemic in this region, and it's a climate-sensitive disease. So the increase of both temperature and precipitation create more opportunities for the breeding of the mosquito vector that transmits the disease to humans. Now you can see on this figure that precipitation, minimum temperature, and dengue incidence all increase when there are El Nino events. And actually, ENSO was found to be the most significant predictor of dengue fever in this region among the three: precipitation and temperature. So at the end of 2015, when a really large El Nino was ongoing, together with a colleague of mine who models infectious diseases, we combined the real-time forecasts of minimum temperature and precipitation from a seasonal forecast system and the real-time ENSO forecasts for 2016 into a model for dengue that she developed and issued a real-time forecast for dengue for the whole year, from January to November of 2016. And we verified the forecast at the end of 2016. And what we saw is that the prediction framework was behaving very, very well, because it managed to predict that the the dengue incidence would substantially exceed the mean of the previous 5 years for the peak dengue season. So here on the left, in the figure on the left, the prediction is in dashed red line, and the observation is in dashed blue line. And then at the end of 2018, we repeated this exercise, but for the at that time there was a mild El Nino ongoing in the tropical Pacific, and we wanted to test the prediction framework for in this kind of conditions. And again, we predicted the climate variables in real time, and we used this for the forecast of dengue. And we were successful in showing that the dengue incidence would not exceed this time the mean of the previous 5 years and would actually stay well below it, as you can see on this figure. So to wrap up, there are some conclusions of my talk today. So one is that the statistical ENSO prediction models still need to take advantage of the availability of subsurface variables such as temperature, which are provided regularly now. And that temperatures at different depths and regions of the tropical Pacific are good predictors of ENSO, along with sea surface temperatures and zonal wind stress. And we could issue a skillful prediction of the Nino 3.4 time series with our model and predict the strongest events up to 2.5 years in advance. And the amplitude of the biggest events were much better predicted after 1994. And we established that this was due to better observations after that. And finally, we used real-time and union forecasts with the model in a prototype for an early warning system for dengue in Machala. And the prediction system successfully distinguished the dengue risks both in years of strong El Nino, but also years of weak El Nino. Thank you. And here I have listed some of the relevant papers that describe the work I showed in more detail. Thank you very much.
Well, thanks. Opening it up to the room. I don't see any questions online yet. Any questions in the room?
I have a question about, can you hear me?
Yes.
Okay. So I have a question about the performance of the statistical model prediction for the after the 2016 period. So you train the model before 2016 period. What about after the 2016? How does it do?
So the model was trained for the period before each forecast was made. So this is a very interactive model, which actually the components of the model are re-estimated every time you issue a forecast. So I don't know if this is the question or.
I was just wondering whether you evaluated the real-time forecast after 2016, because before 2016.
No, so the what I showed were hindcasts, and only the real-time forecasts were only for 2016 and for the period after that, for 2018-19.
Right, and how well did that do, the real-time forecast?
The real-time forecast.
Yes.
Okay. For 2016, for this event, I think I had it in the presentation. It actually did very well even for very long lead times. For 2019, it overestimated the event a little bit.
Okay.
So I don't have a figure to show that, but yeah, it did overestimate a little bit the El Nino that developed.
Thank you. I think I missed some of the time label of the plot because I'm sitting a bit far behind here. Thank you.
Yeah.
Okay. I also have a question for Desislava. Thank you so much for your presentation. So you stressed the importance of having subsurface observation for your prediction of ENSO. Which quantities do you specifically use? Do you use like temperature at all grid points, or do you, or wherever you have observations? Do you use like thermocline depth, heat content in some part of the tropical Pacific? So what do you usually include in your model?
So this is explained very well in the paper, which I can share. But basically, what I used was average temperature at different depth levels. So I extracted indices from boxes in the subsurface. Only temperature. I haven't used other variables. And at different lead times, so I take the peak of El Nino to be in December always, which we know it's not true, but this is how it's done in the model. And I use different predictors in the subsurface based on how many months before December it is.
There's an online question from Anka. Go ahead.
Thank you. Same topic. I'm curious to think about taking this forecast to the next step from the prediction of ENSO to the prediction of incidence of dengue and presumably some kind of action in the user space. And going back to the verification of the real-time forecast, given that issuing a forecast of a particular prevalence of a dengue fever will modify behavior and therefore will modify the outcome, is there a methodology that is credible and has the trust of users to demonstrate that it is the intervention that caused the change in? So the correlation between ENSO or your prediction and the number of cases will break by the very nature of having issued the forecast. What's the methodology that is typically used for this, and are users buying it, so to speak?
So this framework is still in development, but the people in Machala actually are considering it, and as a result of this, they started using climate information in their tracking systems for dengue. So if I understand correctly, your question is if you can show that the prediction of dengue really improves because of the climate variables. Is that what you? The thing with the climate variables is that this long lead prediction of ENSO and the relatively and the seasonal predictions of temperature and precipitation give the opportunity for longer lead predictions of dengue. So in principle, nobody issues dengue predictions at lead times of more than 2 to 3 months in this region. And this gives an opportunity to have a prediction at almost 1 year or 12 months before, which is useful for planning costs for taking measures for controlling mosquitoes or breeding sites of mosquitoes and things like this. In this case, this is still an ongoing work, and so far for these two events, we saw that we have pretty good forecasts. But yeah, I can't really say more about this.
But I think we should think of methodologies to demonstrate whether the forecasts were good or not. So when we do use them in reality, and therefore people take measures and mosquito numbers are down and dengue cases don't happen, even though the climate drivers were active and were well predicted.
Mm-hmm. Yeah, it's true.
Thank you.
thank you. This is question for Amelie. Yeah, thank you for the presentation. Now I know how does the Colorado River Basin prediction system runs. I understand the ESP. Yeah, I do not understand the climate ANN. But I'll ask you that question. So by design, your forecast system is only able to capture the initial condition effect. You did not design the system to incorporate the climate forcing or the climate anomaly effect. So you did not get any skill as you go away from the like initial condition effect at the longer lead time. So do you expect improvement in the skill if you incorporate the climate projection from something like a Smiley run or something like a subseasonal forecast? That is first question. Second one, from yesterday discussion, we learned that, yeah, there may be some other variable that can provide a better predictability. Like there was a presentation where soil moisture type of variability was better correlated with the stream flow. So in that case, like, is there, I know you are using the stream flow forecast as an input, but instead of the stream flow, if you use some other like a total soil moisture or the soil moisture as the input, do you expect the improvement?
Thanks for your question. So I realized I didn't go into the details of the Streamflow forecast as much as I had meant to. So ESP is created by a hydrology model that is then run with time series of precipitation and temperature. So it inherently has information about soil moisture in the model specifically. The CLIME-KNN method that weights ESP forecasts with NMME 1 month and 3 month precipitation and temperature forecasts, as well as with antecedent flow conditions from the past 3 months. And so, so we are including in that CLIME-KNN method some information about future climate S2S scale forecasts from NMME. And we found in some months that did provide more skill, but in the Colorado River Basin, it's a little, the skill of these large scale models don't necessarily always, aren't necessarily strong, I guess. So we were trying to use those where we could find some sort of skill incorporated in them. That antecedent or the previous months of flow, the idea of that was to try to get some information about the soil moisture inside or with that predictor. I can't remember if we specifically use soil moisture or not when testing different predictors, but that was one way to try to get some information about the current basin conditions in that as well.
Any other questions or anything online? All right, we'll go to break. Maybe Matt, if you want to tell us when we're back.
Yeah, I think we're basically okay on time. So let's come back when we were scheduled, 10 after 10 Boulder time, so 20-minute break. And we'll go through the final session at that time on current and planned multi-year prediction capabilities.